Thank you very much for the introduction. So I'm Robert, and this is work with a whole bunch of co-authors that I'm going to specify by name. So separation logic, that's one part of the title. So since this is not the International Conference of Separation Logic, let me give you a one-slide introduction to separation logic. So a key difference between separation logic and ordinary logic is that propositions that denote ownership of resources. And that becomes most evident in the separating conjunction operator of separation logic, which is a bit like ordinary conjunction, but not entirely. Apart from saying that both P and Q hold, it states that P and Q should hold for separate resources. So this becomes evident in a OR triple, like this one, for the swap function, which takes two memory locations and then swaps their content. So in the precondition, what we see is that we also use the maps2 connective of separation logic, which states that location x1 has a certain value and location y has a certain value, and then afterwards they are being swapped. Now the significance of the separating conjunction is that by that we know that these two locations are different. So this very simple idea of separation logic turned out to be a very good one. So separation logic is used quite a lot. So if you come to any of these conferences, you always see like a couple of papers about it. So the nice thing about separation logic is it provides a very high level of modularity and scales to all kinds of fancy programming language features like concurrency. And if you look at just implementations of separation logic in the COC proof assistant, there is a growing collection of them. So as we see here, there is an interest in separation logic. There's an interest in doing separation logic in proof assistants like COC. So let's take a look at what we usually have to do whenever we make our new separation logic and we want to somehow use it in a proof assistant. So first of all, we have to prove that the logic is sound. Because, well, if the logic is not sound, what's the point of it? Second of all, we typically want to use the logic to carry out some proofs about programs or so. So for that, you typically want to develop some kind of tactics to carry out these proofs. And what's the issue here is both of these steps, they are quite tedious. So a thing that we have been wondering about for the last couple of years is, can we somehow simplify these steps? So before coming to the actual contribution of this paper, let me give you an overview of some prior work that's very much related to this, namely the work on Iris that we have been doing with a large network of collaborators. And after that, I'll come to the actual contribution and in which ways Iris still falls short. So Iris itself can be used as a very nice way of simplifying this process of proving soundness of one's separation logics. And apart from that, we had work on developing tactics for Iris. So let's go through that. So Iris is a general language-independent framework for modeling your own domain-specific higher-order separation logics. So what does all of that mean? So general means that if you look at all of these separation logics that have been out there, in there people have been developing all kinds of different reasoning principles, and in Iris we try to somehow unify these principles so that they could all be derived from simpler terms. It's language independent, so the framework is parameterized by the programming language, and you can instantiate it with Rust, ML, or whatever you like. But more importantly, Iris can really be used as a framework for modeling your own logics. And we have been doing that quite a bit. We have used it, for example, for modeling the IGPS logic, which is a logic for weak memory consistency, and some others that are listed here on the slide. Then, of course, whenever we want to do proofs in Iris, we need some machinery for that in COC. So if you define your logic this way, then, well, you get soundness and so on, but then the question is, how do you do proofs in Iris itself? So for that, we developed a tactic language, which we called Iris Proof Mode. And this here is a demo of a very simple lemma in Iris and a proof using Iris Proof Mode. So for those of you that have ever seen a COC proof, probably the first thing that you will notice that is pretty much the same as a normal COC proof, with a couple of small differences. So first of all, this thing does not denote a statement in the COC logic, but in the Iris logic. And that's signified by the fact that we are not using implication and conjunction, but instead we are using the separating conjunction that we have seen before already, and the magic wand, which is basically like the separation logic version of implication. So here this is not a lemma in coq, but a lemma in iris. And then if we look at the proof, then we see this is also pretty much like a proof in coq, but now all of the tactics have been prefixed with an I. So instead of intros, we have I intros. Instead of destruct, we have I destruct. And the key thing about iris proof mode is that these tactics behave pretty much the same as the normal coq tactics. So what you see after executing the first two tactics, we see we get an additional context with our separation logic hypothesis. They're all named by the means of the names you have given in the tactic script, and you can carry out your proof as you are used to. So now there is one big difference. The goal that we are trying to prove is not a normal conjunction, but a separating conjunction. And the thing that I told you about separating conjunction is that there you have to subdivide the resources. So now when you want to introduce it, you don't just use the split tactic of coq, but the I-split tactic of iris, which takes as an argument the way how the hypothesis should be subdivided. So in this case, after we execute it, then we see that the context here has been split up in two parts for the two different subgoals. And then we can finish the proof as we would expect. Of course, this proof here is very elaborate, just to demonstrate how it looks like, but you can also kill it automatically using one tactic. So, wrapping this part about iris and iris proof mode up. So what are the good things about iris proof mode? Well, it enabled a whole bunch of papers to have mechanized separation logic proofs. And the reason why they do that is because the proofs in iris proof mode, they really have the look and feel of ordinary coq proofs. So basically for each tactic in coq, there is like a variant for iris. Second of all, it supports a lot of advanced features of separation logic, which was crucial in many of these developments. And while the example here was just about proving separation logic entailments, it can be integrated with calculus for weakest preconditions and associated tactics. The next talk after mine will go a bit more deep into that. So of course, whenever there are good things, there are also bad things. And the bad thing about iris proof mode was that it was tied to iris. And I will explain in a bit why that's a bad thing. So basically, if you look at these two steps that we were considering, namely proving soundness, and second of all, having tactics, we really would like to decouple that so that the tactics are not tied to the means that we have used for proving soundness. So that is what this talk will be about. So let me first explain the kind of problems that we have and why we really want to decouple these tactics from iris. So the first issue with iris is that all the propositions in iris are affine. And that means that you can just forget about resources. So here there is a very simple example of a Hoare triple where we read from one location and assign it to the other. And what you see is in the precondition there are two maps2 connectives, namely for location L1 and L2, and in postcondition there is just one. This thing is provable in iris, and in some languages you may not want this to be provable because you may want to be able to precisely account for the resources that are being used. And here we are just forgetting about the location L1. The reason that you can do this in iris is because it has this axiom hardwired in. P star Q entails Q, which basically means you can always forget about some resources. And this axiom is not just hardwired into the foundations of iris, but also into many of the tactics of iris proof mode. Namely, the most obvious tactic is I clear, which allows you to just drop a hypothesis. The other one is I assumption, which whenever you want to prove a goal and it appears somewhere in your hypothesis, it will just drop all of the other hypotheses. And the fact appears in more tactics, but these are the two most simple ones. So what is the issue here? Not having this axiom is in fact useful because it allows one to give more precise accounting of resources whenever you are dealing with a language in which you have an explicit free operator. So the challenge that we have here is how can we somehow disentangle this axiom from the iris proof mode tactics. Apart from this problem that iris and iris proof mode have this affinity axiom built in, there's yet another problem with the setup. So there is not really support for reasoning in these derived logics. So you can use iris and iris proof mode to define your own derived logics, but reasoning in them, that is more of an issue. So let's see why. So iris itself is defined in terms of the coq logic. So whenever you are reasoning in coq, with propositions pop, then you can use the standard coq tactics. And whenever you're reasoning in iris, using the propositions iprop of iris, you can use all of these iris tactics, these I intros and ID stroke that we have seen before. And then there are also means for dropping down whenever that's necessary. What happened in some of these works, like the IGPS logic, where we built yet another logic on top of iris, is that we defined the type of propositions, in this case IGPS prop, in terms of iris. And then basically you get like a separate logic which is modeled in terms of iris, but all of the connectives like the separating conjunction and so on, they are different. And then in that case, well, neither the coq tactics apply nor the iris tactics. So the question is, how can you do proofs in such derived logics? Well, that is the contribution here. That is MoSeL, the title of our paper. It's also a wonderful river in a Rhine region in Germany, hence the picture. So what is MoSeL about? It's a general extensible model framework for interactive proofs and separation logic in coq. And what are the key contributions and key features of it? So all of the tactics here, they are parameterized by some general abstraction of separation logic. It supports reasoning in both affine separation logics and general separation logics and combinations thereof. It supports reasoning in these derived separation logics, as I've explained before. And on top of that, the kind of thing that you get is whenever you have all of these different separation logics, they have all kinds of other connectives of their own. And using type classes, you can fine-tune the entire system to basically instruct it how it should deal with these logic specific connectives. And apart from that, we showed that it's actually usable in practice. We have used it on 5 very different existing separation logics that are listed here. So let's go to the first step. We somehow want to make all of these tactics of iris proof mode, we want to turn them into MoSeL tactics. So the thing what we want to do there is we want to make them logic independent. And for that, we need to have some kind of an abstraction of separation logic. Such an abstraction, fortunately, already exists for 20 years, and it's called a bunch implications logic. So what is that? It is some abstract type of propositions with all of the operators of intuitionistic logic and the separating conjunction of star together with its identity amp and its adjoint wand, satisfying the axioms that you would expect. In coq, we can model this using a canonical structure, which is kind of like a type class. And there you see there's like the carrier for the type of propositions, the entailment relation, and all of the connectives together with their axioms. Whenever you do this, you can already get like quite a while. So let's take a look at what we can do. So the thing that we can do now is we can state our lemmas in terms of any logic that is a BI. So I talked about this IGPS logic, that's a BI. So here, as you can see on the thing on the left, here we have a lemma that holds in the IGPS logic. Also, what we can do is we can prove lemmas for any BI out there. So in the lemma on the right-hand side, we are basically quantifying over any BI logic. And as you see here, the tactic scripts, they're all exactly the same. And they all behave as you would expect. So just making these tactics parametric by such a BI logic is not enough. There is, of course, more to it. So I discussed these 2 problems. So let's take a look at the first one. How can we disentangle this affinity axiom? So this is this axiom that allows you to just throw out propositions that holds in iris, but that does not hold in some other logics. So the poor man's solution to this is very simple, but also not sufficient, as we'll show. Namely, you just make 2 versions. One for affine logics, like iris and IGPS, and one for non-affine logics, like CFML and CHL. But of course, making 2 versions of all of these tactics, that would be pretty stupid. Because first of all, it's duplicate work and duplicate maintenance. So that's not nice. But even more fundamentally, there is a problem. There are other logics out there that mix both affine and non-affine resources. So you could imagine that you want to reason in a precise way about resources in a language where you have both garbage collected pointers and pointers that you have to free manually. Then you would have 2 such points2 connectives, one that's affine and one that's not affine, depending on whether the location is garbage collected or not. And then one you would want to be able to clear out and reason with like an iris, but with the other not. Another example appears in the paper by Tasserotti and others where they have some advanced things using ghost state, where some ghost state is affine and others is not. So how can we support that? So the key idea that we have here is that we do not want to classify whether the whole logic is affine, but instead we do want to classify whether individual propositions are affine. So how do we do that? Well, we define what it means for a proposition to be affine. So the definition here is P entails AMP. And depending on the BI logic that you are using, AMP will have a very different meaning. So in the case of Iris, this thing is vacuous. Every proposition is affine. But whenever you use classical separation logic, then pretty much no proposition is affine. And whenever you use this mixed logic, this will exactly classify which propositions are affine and not. And then we can quite easily change all of these tactics to just have affine side conditions. Namely, whenever you want to clear something, then the thing you want to clear should be affine. Whenever you want to use assumption, then the remainder of the context should be affine. So how do we do this in Cork? Well, we use a type class. And using that type class, we can express what it means for a proposition to be affine, and then we can make instances of it. For example, we can declare that our garbage collected maps to connective is in fact affine, so then we can clear it. And we can declare an instance saying that whenever two propositions are affine, then taking the star of it is also affine. So this way, we can nicely and in a generic way deal with propositions that are affine and those that are not. Now, you may wonder, if you look at the title of the paper, then there is something called Modal in there. So what about modalities? What turns out is that corresponding to this class of affine propositions, there is this affine modality. And this is a unary connective. It's defined as being P conjunction AMP. And intuitively, it's expressing that the proposition holds using just affine resources. And this modality is very useful because you can take any proposition, turn it into an affine one. It commutes with all kinds of operators, and it gives rise to an alternative classification of affine propositions. And whenever you want to reason about affinity, as we show in the paper, this modality is pretty useful. More importantly, this whole idea of carving out classes of separation logic propositions and defining their corresponding modalities is not just applicable to affine propositions, namely the propositions that you can throw away, but it's very widely applicable. Here, there's a whole class of different, a whole list of different classes of propositions that we have identified, both in just general BI logics and in more specific logics, and their associated modalities. In the paper, we show how you can modularly deal with these classes and how you can use them in general purpose tactics for separation logic. So, that's it. This was my presentation of MoSeL, which apart from this wonderful river is also the system that we have developed. And to sum up, so MoSeL, it's a tactic language for separation logic proofs in Cork. It's parameterized by a general abstraction of separation logic. It supports both general and affine separation logics. It supports reasoning and derived separation logics, and it can be totally fine-tuned. We have used it on 5 very different separation logics. You should try it too, and then we can add your separation logic to the list. That would be great. Thanks.
Thank you. So there are 2 questions on Slido. First, Jasper asks, do you have to implement library functions twice for the affine and non-affine propositions, or do you have some kind of affine polymorphism?
So I'm not sure what you mean by library functions, but basically the point is that all of the tactics for which it matters whether something is affine or not, we don't have two versions, but they are just parameterized in a very fine-grained way whether a certain proposition is affine or not. So depending on the logic that you are using, the tactic will be more widely applicable or not.
The same tactic for both?
The same tactic for both, but it's parameterized.
Okay, thank you. So another question is, what about customizable proof automation ranging from auto to cross?
Sorry, could you repeat it?
Yeah, what about customizable proof automation, like Cox, auto, and cross tactics?
So what about customizable proof automation? So basically what you can do is all of the MoSeL tactics, they are just LTAC tactics. So you can use Coq's tactic language to compose the tactics and to turn it into more automated ways. Apart from that, MoSeL itself provides some general purpose tactics like iframe, which is doing framing, which is a very widely method for semi-automating parts of proofs and separation logic. It can also be combined together with Coq's auto tactic. So we have instructed Coq's auto tactic to also handle all of the separation logic connectives. So you get all of that for free whenever you instantiate it with your logic. And then of course you can also tweak auto entirely for your own logic connectives.
Great. So a last one is, can I define a bad in some way tactic in MoSeL, or do you have a type checker that checks what you're defining?
So the question here is, I suppose, whether MoSeL, whether that increases the trust code base of Coq. No, it does not. So basically what happens is all of the MoSeL tactics, they are proven sound with respect to the BI axioms and with respect to whatever information is in all of these type classes. So whenever you have a MoSeL proof, then that really implies that you have a separation logic entailment. And whenever you have proven soundness of your separation logic, that really means that it enjoys whatever property your separation logic is guaranteeing.
Okay.
So it really gives end-to-end correctness.
Okay. Thank you very much.
Thank you very much.